The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker, gentleman Neal Berke, was at the time working for W.R. Grace in charge of their research labs, and now he's working with Tourney Consulting. But Neal and Richard, I think, go way back. So it's a pleasure to have him join us today as part of the program. So Neal is going to talk to us about using large-scale specimens in the lab to develop field evaluation techniques for concrete. Thanks, Neal.
Thank you, Michael. Yeah, it is a real pleasure to get to speak at a symposium session in honor of Richard Wires. As Mike indicated, I've known Richard for, in Mike Sprinkle's terms, for over 3 decades. So it's a pretty long time. And like Mike, I first met him as part of the SHARP program, I believe. I might have bumped into him maybe a year before at TRB, but basically in the SHARP program, I worked with him and learned a lot. Him being a professor, learned a lot from him. We had a lot of fun at 2 o'clock in the morning, 3 o'clock in the morning, looking at bridge decks. But I mean, and I even sent some of my guys working for me to hang around with him so they can learn something. So it's a real pleasure to be here. Today I'm going to give a brief overview. Here's an overview. I'm going to give an introduction about obviously what I'm talking about now, and then review of the techniques used to determine corrosion rates of in the laboratory, and need for accurate field measurements. I'm going to suggest that large-size laboratory specimens can very much are much more likely to simulate larger field structures. A lot of these little small specimens are good for product development and to get some ideas of things. But if you really want to look at techniques, most of our field structures are measured in square meters or square feet, and we need something maybe a little bit larger. It's also, if you get the right size large specimen, you can still do some of the laboratory techniques on them. So you can correlate something that might be user-friendly in the field to something that's more rigorous in the lab. And we'll talk about that. And it turns out that corrosion potential mapping is one of the better ways of doing that. And it's a quick technique, can evaluate very large areas at a time. If you're trying to do polarization resistance, or some of the other types of ways of measuring corrosion rates out in the field, you know, realistically, if you have a corroding spot, maybe 5 or 10 minutes. If it's not corroding, you really should go 20 minutes, even though people tell you you can go less. So if you really are talking about large amounts of times at small spots, if you want to shut the traffic down for days, you can get a very good idea of what's going on. So me coming from industry rather than being a professor, a little bit of practical bent, and I got a little bit of that practical bent from one of my professor friends named Richard. So that's one of the things we want to look at, and I will pull off an example from work we did with Richard back in the early 90s so to prove that I actually knew him back then, and it'll be, we'll talk a little bit about that. Also, I want to mention that in the first slide had some of my co-workers on this, Brooks Bucher and Kristen Adey, and we're training Kristen to be a corrosion engineer. So even though she's not in school anymore, she is getting some training. So once again ties into what Richard has done, is teaching people to go forward. Now the problem, assessing corrosion activity in the field, as I mentioned, provides information on the current condition. You got to remember, you go out and measure the corrosion rate today. You know what it is today. Tomorrow it might be a little bit different. It might have been different last year. So if you're going to start doing that, one would suggest that one does this periodically at roughly the same times in the year or same conditions, and then compare these to each other over a long period of time. That'll give you an idea whether or not it's just a spike or it's continue going up or staying steady, and then you can use that then to predict your future time. I mean, why would you want to measure corrosion rates? If you've got rust coming up through the concrete deck, you don't have to be a corrosion scientist or an engineer to know you have a problem. And if you got cracking due to corrosion with rust coming through the cracks, you know you have a problem. What you really want to know is what's happening to that deck that looks okay, but you know it's had several years of chloride applied to it, or the pile that has several years of chloride, but so far it looks okay. So you really want to get an idea of finding out when my bridge management system, when am I going to have to come out and start planning repairs on that. And the best way to do that is to get some idea of the corrosion activity before it goes into heavy corrosion, so you can start predicting that. Now, obviously, in the field, you got traffic control problems in limited time. Worked several times outside in the field, but I mean, it's always fun just working on the deck and having the cars or the cars aren't so bad, but the 18-wheel semis going 90 miles an hour full of oil, those always give you a fun thing. And I've had one time I was on a deck where we ended up tying our potentiostat to the guardrail because when one of these over tankers came by, the thing was actually bouncing, and we was able to measure the frequency of what you get in the deck for another experiment I needed, and we had several repetitions before the vibrations died down. So it's not fun traffic control. Plus, it's costly to people. I mean, from the green point of view, cars staying in traffic, putting out exhaust, and replacing it, that's something that you really don't. It's a cost to the consumer as well as a cost to the actual out-of-pocket cost to the DOT. So many laboratory techniques, as I mentioned, are not practical. There's time constraints. Yes, you can go out there and do polarization resistance testing, and it's going to take you, do it right, 10 to 20 minutes a point. And if you want to cover a couple, 1,000 square feet, 100 square feet, you're going to be there for quite some time. And it's only going to tell you what's going on right where you're at. It's not going to tell you what's going on over there. So you have to guess. Even if you put a grid up, you can miss things in between the grid. There's also the problem of uncertainties, how much steel is affected. They'll tell you there's some devices that have guard rings, so they work okay if you're right over a highly corroding point. If you're a little bit away from corroding point and passive steel, it spreads out. So you really don't know, you really don't have a good idea of how much area you're looking at, and you can't cover enough area to begin with. So what we need is a relatively quick but accurate method. Good enough. Good qualitative assessment is good. So maybe, engineering, if you're close, might be good enough to tell you what you need to do. So in Richard's, as Mike pointed out, that might be a good place to start off. You could get semi-quantitative or quantitative out of it if you do a little bit more work. And then, of course, you can, now that you've identified areas that are corroding more rapidly, you can now come back and do those few areas with a confirmation with a more accurate measurement of corrosion rate measurement, and then that as a confirmation and an idea now what your rates are. But you go to where you need to go. You're going to be much more. It's kind of like you're going to know where to do your more detailed analysis. Now, lab techniques. We can spend a lecture on each one of these, so I'm just going to go over what some of the ones are. You have electrochemical techniques that are non-destructive. You can do corrosion potential measurements, and that's simply taking a half cell through a voltmeter, high impedance voltmeter, through another end tied up to the rebar. You measure the corrosion potentials. That's fairly simple to do. It doesn't give you by one corrosion potential measurement by itself. It doesn't tell you the corrosion rate, but it gives you an idea of what's going on. Polarization resistance, which would give you a corrosion rate, works quite well in the lab, and you can correlate it to what you see on actual corrosion samples. You can get real fancy electrochemical impedance spectroscopy and some variations of that, which work very well in a lab. They could take a little more analysis as needed. In the field, they're a little bit more tricky to run because of the currents at different frequencies will cover different amounts will go through different amounts of concrete. And then you have a lot of the macro cell techniques that people use in the lab, but in order to do that in the field, you'd have to have all your bars individually not attached to each other so you can measure the macro cells. And that would not be good in case you want to use cathodic protection later on to save something. So that's also totally impractical to build a deck like that. So basically, these are good lab techniques, which you can use them, as we'll show, combined with some to correlate between each other where they might be useful on a larger slab or column. Now, other techniques obviously got mass loss. That's destructive and totally impractical for a field measurement. Visual appearance of the surface, as I mentioned before, surface staining and cracking. We're all experts there. And anybody that sees the laminate, sees concrete spilling off, rust coming out, cracks, with rust coming through it. If you can't tell that there's a corrosion problem under that, then maybe you're in the wrong room. So that's basically, so they're pretty, so at that point I would say it's a little late. Maybe my DLT guys will disagree with me. I think you want to know what's happening before that. But those definitely will get on the list to be fixed faster. And then you can do a detailed microscopic analysis after you break the things open. You do photographic analysis, and if you really want to get into mechanisms and what's going on, you can get it under high power and look to see what's happening, which might be useful for some of the stainless steels, especially with an EDS system. Now, doing the corrosion rate measurements. Here's my colleague, I believe that's out there in the field, and he's doing polarization resistance with a ring, guard ring, and you can see he's got one little spot there, and he's going to be there for 10 to 20 minutes or so, getting that spot ready and taking the measurement. And you can see there's a lot of cracking here. There wasn't a whole lot of corrosion in this particular one, but there was a lot of cracking. It was early on. Or you can do corrosion potential mapping after you, and you got to do this right. You got to get the deck wet the night before, or whatever you look at wet beforehand, and then make sure it doesn't have puddles of water on it. You don't do this on a dry piece of concrete. It's got to be something else I learned from Richard. And if you take too long to do it and the sun comes up, the numbers will start changing. So you have to move fast. Fortunately, you can move fast with this technique. So the amount of time it took to get that one little point, here you're measuring this whole area in a few seconds, maybe a minute or two. So it's much, much faster. So large-size laboratory specimens correlate potential map and corrosion activity. One of the nice things is you start doing some work for some other project, and you realize it's got some implications beyond what you were working on. So it'd be nice to have a large specimen to be used to evaluate corrosion potential measurements versus other laboratory techniques. Now, we were doing a large study for the U.S. Bureau of Reclamation to develop a repair protocol for determining different corrosion mitigation technologies, both topical repairs and integral repair methods. And this involved 40-inch by 40-inch slabs, basically a meter by a meter. So they're large slabs, 5.5 inches thick. 6 number 4 bars in them, so it's pretty dense on the top mat. And then we had a heavy wire mesh to provide a cathode for the macrocell corrosion in the bottom mesh. And we did cyclic ponding with sodium chloride. And to give you an idea what these slabs look like, here is the core. And we had an area on the, is there a pointer on this? Or? Yeah, we had an area over here where we can measure the relative humidity of the concrete, the resistivity of the concrete, and an area to take cores for chloride analysis. So it's outside of, so you're not disturbing the bars, which was nice. And we had 105 of these things. So talking about having lots of replicates, we had a fair amount of samples to look at. This is kind of all wired up, but the nice thing is you can wire them up so you have everything coming to a nice thing about a lab, which you necessarily can't do in the field, but you can bring everything to a nice junction box, and then you can easily plug in things and measure what's happening between the individual bars. Each bar, we were able to measure the current on each bar separately from all the bars on it. So we could tell some of these bars would end up being anodes and some would be cathodes. So we had a cathode from the bottom mat and a cathode from several of the other bars. Just like you get in the field, not all the bars on the top of a concrete structure are corroding. Typically, if you'll find that you'll have several bars that have corrosion, and one's right next to it, or even on the same bar, it looks absolutely pristine. This picked it up. We used ready-mix concrete, none of this labcrete. So the ready-mix concrete trucks came in. We cast 20 of them at a time, but we theoretically could do more. And something else I learned from Richard, where he did a lot of his samples were ready-mix concrete, making large samples. So, I mean, it's amazing what I think about what I actually learned from that guy. I won't get into some of the other things I learned from him, but we had ready-mix concrete here, and some of my colleagues are putting it together. And you can see you're using normal vibrators and finishing techniques to put these things together. So this is, it's lab concrete built built with ready-mix concrete, and just to notice, this is a ready-mix truck we can pull into our place. We have enough space there to make these large samples, and any time of the year. It's climate control. Used to be we're in an ex-GM plant, so we have real tall ceilings, high air movement out of the place. So we're allowed to have we can have a truck in there. Corrosion monitoring on these things. We did corrosion potentials, ASTM C876. We did macrosol corrosion currents, mat-to-mat resistance, electrical resistivities, chloride profiling, internal relative humidity. I said future there, but some of these we did measure the relative humidity on to get an idea of some of the mechanisms that might be going on. We did, I don't mention here, but we did do some polarization resistance on some of them just to see what was going on, but it didn't really add anything more than we knew. You can see the amount of equipment we had for everything. So the junction boxes make life real easy when you have hundreds of these. You just come in, you get all the switches, and you can isolate each one, and you can get macrosol currents, the mat-to-mat resistances, corrosion potential readings, and electrical resistivity with the runner on the outside. And here's just to show you that we really did have lots of these. This is one of racks back to back, and we have a couple more like this here. So we really did have lots of samples, and there's one of my co-authors actually doing some of the measurements. Take the measurements, and you can get a potential mapping, and you can see that there's some areas. Typically, with potentials, the best thing to look at is the contours. You can see there's in a control sample that went into heavy corrosion. There's a lot of corrosion was taking place, indicated here and here and here on the bars. A sample that was not corroding at the time was very clean. Now, the reason to look at these over time, this one was one that we repaired, so when you opened it up, it still had corrosion on the bars because we applied a repair process after it looked something like this. So you just can't come out and do your measurement at one time and say you got everything. You really got to follow it over time, in case and it gives you a better idea. And I'll give you a little more evidence of that. Here's one that we're all experts on. You can clearly see from the outside there's a fair amount of rust coming through on this sample. And this is not, needless to say, this is one at a relatively low cover, and we've gone to higher cover since then. But you can see, once again, we have our corrosion potential map. It would indicate that this bar over here is doing something pretty bad, and this one over here. The bars in the center would have been a little less going on, at least at the time of the measurement. When we measured the integrated current on all of them, sure enough, the bars there in the more red areas had much higher coulombs. And you had the two lower, and also had more negative potentials, as you would expect. Still some rust on the bars that had no coulomb readings, because once again, that's only measuring the macrocell. You do have a little bit of, you can have a little bit of localized corrosion going on. That's not, that doesn't need a macrocell from somewhere else to feed it. And but overall, you look at that, it's still much less corrosion than the other bars. If you have macrocell feed, if macrocells are going on, they're going to lead to high corrosion rates. Looking at some newer samples we made, this time we got them a little bit earlier in the game. This one had a little bit of activity on the bar over here, this number 2 bar initially, and then it came down. And this here we're measuring current, but so there was a little bit of current for one small time. It self-healed, and then nothing happening. Another 5 bars on it, and another 5. We had 5 specimens of each. Other 4 specimens had nothing. So basically, this is a nice clean map. Nothing's going on. In this case here, we have 1 bar that really took off. That's this bar over here. The other bars are pretty benign, and you can see you have a high corrosion, real high contour coming into this region. Now, the reason you want to look at contours rather than necessarily just the absolute values, all these values are fairly negative. You say, hey, it's corroding everywhere. We know it's not corroding everywhere, and what happens is, of course, if this one is, this bar here is corroding rapidly, these bars are a cathode, they're going to have a mixed potential between them, and they're going to come to a more negative value. So this reading, a corrosion potential reading by itself, might not give you everything. And then we have another case where we have several hot spots here and here. That's this bar and this bar. And we have a couple more over here, which is some of the other bars. So once again, looking at the potential map, we can pretty much tell which bars are showing the most amount of corrosion. Okay, that's good. I only have a couple slides, so we're perfect. Get back to what I did with Richard, and I think Richard actually does this one, but it's in the same paper that I'm a co-author on, so we'll take partial credit for it. and I replotted the number. I replotted it with a fancier plotting program, contour program that I had and for the other ones, and what we had for the paper back in '91 and '92, and. You can see hot areas over here. This was the side of the bridge where all the icing salts ended up getting pushed to, and this is more north towards the center. You can see we had an area that was about 26 feet by 12 feet that we were looking at. Richard came back and measured the corrosion rates, the 3LP method, and you can see they're high over here where we'd expect them to be high. They get lower as you get away, and then they're much lower down here in the benign region. So in the actual field, they work quite well. I think taking this entire potential map took less time than probably one point here. So you think about it. So there is some. So it does, match up. What you see in the field does match up. What you see in the lab does take place in the field, and it seems to be an effective technique. So include large laboratory slabs demonstrate that corrosion potential mapping correlates to the corrosion activity as measured by electrochemical methods and autopsy of the specimens. And by the way, we're not the first to show this. There's been plenty of work at this in the field. As I said, we have a nice lab technique now to correlate that better. Where correlation to the field was shown, the potential map can be performed in only a few seconds per measurement point versus 10 minutes plus for polarization resistance or similar techniques. And I think that's a real strong point. And thus, potential mapping is a practical means of evaluating corrosion performance in the field. And that's it. Thank you.